Okay, I'm going to, in this video, look at a thing called retrospective and prospective studies and how we use logistic regression for them. And they're very important in epidemiology, which is obviously the study of disease in populations. So, I want to this is a very wordy slide, but let me see if I can summarize it. We often have what we call a prospective study. So what we do with a prospective study is we will take a load of individuals and we will expose them to some sort of treatment. And then we wait some time and see if things develop. So the classic one we've seen is the beetles. With the beetles, we expose them to concentration of carbon disulfide, and then we counted how many died. The other thing you could do, let's say I want to see if smoking affects cancer or emphysema, which is a lung disease. What you could do is you could take a load of people who smoke and a load of people who don't, and you could wait over numerous years and then see who develops emphysema. And then we could look at the relationship between them by using logistic regression. The problem is that's slow. You have to wait a long time, and often we want to know how things are going. So sometimes we can do what we call a retrospective. So prospective, we start by, observing the people with the treatment going forward, or we could actually impose the treatment if it's an experiment. With the retrospective, what we do is we come and we find people who have, for example, emphysema, and then we look back in time, so we look back retrospectively to see if they smoked or not. So this is good. This is an easy way of doing it. You can go and you can get a load of people with emphysema, and we're going to call those cases. We can go and find a comparative group, sort of same age, sex, stuff like that, without emphysema, call them controls, and then ask them and say, did you smoke or not? The question is, how are we going to adjust our analysis to deal with this fact that we've changed things? Everything we've done has been built on the prospective. You apply a treatment and then you see if we get success or failure. So the nice thing is we can show that with a logistic regression, as soon as we have certain properties, we're absolutely fine. There shouldn't be a problem there. So let's set it up. So we've got our model. We've got our logistic regression model that says the probability of a success given some predictors is related to some sort of linear transformation of our predictors. We take the x, etc. So we've seen all this before. And we're going to introduce an extra variable. So we're going to imagine we've got the whole population and then some subjects are sampled and some are not. And we'll have S is if a subject is sampled, they get a 1 or a 0. And we're going to say that we're going to assume that the probability that you're sampled, given you have the disease or your success, so in this case you have emphysema, and the predictors is row 1, and the probability sampled given you don't have this is row 0. These don't have to be the same rate, but the key thing to do this is that these do not depend on your predictors. You're not more likely to be sampled if, for example, you smoked versus not smoked. All we're saying is that we are going to have a certain probability of you being sampled if you have emphysema, and a certain probability you're sampled if you don't have emphysema. But that is completely agnostic, it's completely independent of whether you smoked or not. And what we want to do is we want to say, well, what's the probability now of our success given your predictor, taking into account that you're sampled? So we've added in this extra sampling. And what we'd like to do is show that this, when we do it, gives us a logistic model, the same as before. Now, I'm not going to go through all the steps of this. It's in the handout. I'm going to let you go through this yourself. We've already looked at one proof where I went through it, and then one proof where I annotated it. This is the one that I'm just going to give you straight as, and you get a chance to go through and see if you can work out how I made each individual step. Okay? So I'm not going to work this through. If you have a go and you get stuck, pop in consulting, ask Matt or myself, and we can go through the steps. But I think you should have a go on your own. But the key thing is, it actually works. The only thing that's different is the intercept. The intercept you can't quite get, because the intercept in your perspective would be the standard rate of getting emphysema, while we can't get that when we've actually sampled in this particular way. So the whole thing is you can use your logistic regression for both a retrospective and a prospective study, which is really, really good because retrospective is a thing that we often want to do in epidemiology. And, when do we use this? really rare conditions. It's very, very useful for rare conditions, specifically cancer. If we want to find if there's a particular cause of a cancer, we can go and find 100 people with that cancer, 100 controls who are similar, and then ask if they were exposed to certain treatments. And the good thing is, it doesn't mean that we have to basically, have thousands and thousands of people that we have to watch over time. We can get these results really, really quickly. So very, very useful. So that's logistic regression. A couple of examples there. Next time, we're going to start looking at how do we start to model other distributions. So in this case, we've done binomial. Next time, we'll look at the Poisson distribution. See you next time.